Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. This is the first show of 2024, so I guess a belated Happy New Year. I don't know if we're still doing that or not really. It's probably we're into February now, so I don't think we can really say Happy New Year anymore. But anyway, I hope you all had good New Year's and happy holidays. So yeah, the usual reminder that if you do enjoy the show, please do consider supporting us through Buy Me a Coffee. It really helps us to keep making the show. Now on to today's episode. I'm really glad to say that I'm going to be joined today by Tamer Eldeeb, who will be telling us everything we need to know about Chablis, fast and general transactions in geo-distributed systems. Tamer is a PhD student at Columbia University and is also a software engineer at Jane Street. So he's very, very busy, I can imagine. Great stuff. So Tamer, thank you for coming on the show.
Oh, thank you so much for having me. I'm really excited.
Well, let's jump straight in then. So I've given you a very brief introduction there, but can you tell us a little bit more about yourself and how you became interested in database management research?
Sure. Yes. So I grew up in Egypt. I studied computer science, and then I moved to the US to start my career in software engineering. That was in 2011 to 2012 timeframe. And as fate would have it, I would start on the Azure storage team, which is kind of a distributed storage database team. And I found that I really enjoy that area. That same year, like in 2012, two very influential papers came out. So during that time, I think the conventional wisdom was generally that transactions are too slow. We don't need them. We're gonna build our all the cool NoSQL stuff, Cassandra and Bigtable and Dynamo, and there were all sorts of these things. And then in 2012, two papers came out, the Spanner paper from Google, and also the Calvin paper in Sigma 2012 on deterministic database systems. And they both kind of showed that actually transactions are still very useful. Even Google developers who are known for being highly skilled were struggling without transactions. And here's a way we can actually build this global scale system. Calvin kind of showed a radically different way that you can do this. And I found both papers very exciting, and since then have been just keeping an eye on the area until I decided to start a PhD myself in late 2019, early 2020. And I didn't intend to work in that area specifically from the start, but I just naturally found myself gravitating to the same area. So.
Awesome stuff. Yeah. So going back on the Azure stuff there, you must have been in there pretty early doors, I guess, then. So kind of how long had the team kind of been going and that sort of project been going when you joined them originally? Because that's kind of feels for like kind of day one sort of stuff.
It wasn't really day one, but it was early. So I think the entire Azure thing started in 2006, the famous project Red Dog. And I think Azure Storage had been in production for maybe a year or two before I joined, or something like that. So it was, it was clear that this is becoming a huge thing. It was already lots of data being stored and so on, but it was also fairly early days. So
no, that's really cool. And also as well, I'm sure a lot of our listeners will be familiar with the sort of the influential Spanner paper and the Calvin paper as well. That's really cool. And I just want to get this over because we spoke about this off before we started recording. And I think it's quite funny as to why you started, why you decided to pursue a PhD during COVID. or during the pandemic. So I'll let you tell the listeners what was the main motivation, what you tried before, and then you're like, nah, screw this. I'm
Oh, I
gonna do
mean, I tried baking like most people did during the pandemic, but I didn't find it very very interesting. So basically decided to just continue working while also doing some research, and it it I like not that I like necessarily recommend it in normal times, but it worked out. So
Yeah, it definitely did, because then when we've got this awesome paper as well to prove it. So let's talk a little bit more about that then. So let's start off, I guess, with a little bit more background, set the scene for the listener a little bit more. So we're going to be talking about geo-distributed databases today. So can you tell us what they are and kind of why we need them, really?
sure. So I think like the definition of a the distributed database is a database that runs on multiple nodes. It's not like a single node kind of thing. And a geo distributed here means that these nodes span geographical regions. It's not like all in the same data center, for example, or the same cloud region. And the reason we need them, I think there's two main reasons. One is some or like many applications are like have users that are geo distributed. Like think about, I don't know, your Twitter or your Facebook or something. Like the users are all around the globe. So you want to keep the data for the user near them so that they can have low latency access to it. Latency is very important. We are all used to like snappy app experience, and like if the apps take too long to load, users just leave. Companies lose money. It's a pretty big deal. The other reason this is also pretty important is just like disaster recovery. Like, you know, I'm sure like your viewers are familiar with, you know, AWS region going down and the internet, you know, stopping to work for a bit or something like that. So for a lot of like mission critical apps, you really want to store like a copy of your data in at least like one more region than like where its home is, probably more. Like hence, like to protect from things like natural disasters that can like happen and take a data center down and so forth. So these are, I think, the two main reasons why you need geo distribution.
Yeah, it's so true. I mean, we're so used to having this instantaneous sort of any application we use these days, right? We just want it to be we're conditioned for it to be like instantaneous, right? And as soon as it's not, we're like, well, I'm not going to use this anymore. So yeah, there's a big thought, and obviously as well the disaster recovery sort of angle as well. I mean, yeah, that kind of speaks for itself, right? I mean, you think one region will be fine, but yeah, what can go wrong will go wrong, right? Murphy's law. So yeah, we need to cover our backs there. So that's cool. So yeah, so as you alluded to when you were like answering one of my earlier questions, you mentioned that distributed database research it's been quite a fertile ground. There's been a lot of work over sort of the last 10 sort of 15 years, especially as people have kind of refuted this notion that transactions, we don't need them, and then everyone's like, hang on a minute, that's a really good thing, let's have those. But how can we do those performant at sort of large scale? So maybe obviously you touched on the briefly, you mentioned Spanner and Calvin, but can you kind of give us a rundown of maybe some of the more state-of-the-art systems in that space and
Sure.
some of the problems that they kind of have still?
Sure. The way that I think about this, and like it wasn't very obvious when I started doing research, but it turns out you can generally like categorize the state of the art systems into two buckets. Like there's fast and there's general, but there isn't both, at least I like until now.
Nice. Yeah.
So in the general bucket, I think like these are your systems that support, you know, traditional SQL. They have this restricted API. They give you very strong consistency semantics. So things like Spanner or Cockroach DB or Yugabyte or like they're all kind of Spanner influenced systems, and they are general in the sense that, like I said, they like give you transactions with all the semantics that you want, like serializability, consistency. You can just like run full SQL on those with all the features. Like there's no restrictions to the programming model, but they tend to kind of be slow, especially like if you have to do transactions that cross one partition. So, like if you can partition your data in such a way that you can like only touch one partition per transaction, you are good, but that's typically not that easy to do. And if you basically have to like run cross partition transactions, you run the well-known two-phase commit algorithm, or a variant of it. Like it's not exactly like it's not always implemented in the textbook form, but it's always kind of like one variant of it. And you take a hit because you have to do 2 RPCs and 2 writes to storage at least for every transaction, and that takes a toll. So that's the general systems. The fast systems kind of look at this and say, okay, two-phase commit is this really slow bottleneck, and we really don't want to do it. So we are going to design the system in such a way that we don't do it. And in doing so, you kind of lose what I call generality. Like you lose a property of the system that is fairly important. So one such property is like the easiest one is like, let's just not have any cross partition transactions at all. Like we will just have we will limit the transactions to a single shard. Or we may let you do transactions that cross shards but with weaker semantics. Or the deterministic systems, which are kind of like structured very differently, that they can be fast and they do support cross-partition transactions, but they restrict the programming model in various ways that are kind of fairly restrictive. Like you either have to, so the code has to be deterministic, which usually rules out things like conversational queries where you are like running a part of a query and then like look at the result and then like issue the other part and so on. And like they do things to like try and mitigate that, but in general you really cannot support like a SQL interface on it. You kind of have to come up with a different query language to fit the system or something like that.
Nice, cool. Yeah, so I liked your trade-off there. Basically, you've got these 2 families of systems, these 2 buckets of systems, the fast ones, but they make some trade-offs, weaker semantics, maybe for cross-partition transactions, restrict the programming model, so we don't have the nice SQL that probably developers are used to. And then on the other side, we've got the general systems, and they take a performance hit for that. When we're talking about a partition here, are we talking about kind of is the physical location of the machine kind of related to these partitions? Are we talking about just
partition in that context usually just means a single machine? It's not exclusive to like geo-distribution. Like even things within a single region have the same trade-offs. Right, I'm just saying, like once you have to like run across multiple machines, you usually have to either like run 2-phase commit and suffer the penalty, or to something else and sacrifice some property about the system.
Yeah, as soon as the network gets involved, right, things are going to get a little bit slower.
That was the conventionalism. Now, I should note that like this category is more about like systems that primarily store the data on disk.
Okay.
In memory systems, like there's been another line of research there, like where you keep your data completely in RAM and you use things like RDMA and so on. And there you could have fast and general, but it's also pretty expensive because it's all in DRAM. And really, I think the popularity of on-disk systems just show that really developers really care about that too. So
Yeah, exactly. Yeah, especially when you start using some of maybe this more kind of fancy hardware or fancy way, it gets expensive, like you said, for one, and also as well, it's not as generally available, right? Like it's not as easy to use. So there's definitely some challenges there as well.
Yeah.
Cool. So we know all the problems now, but we've solved this trade off, this fast versus general trade off with Chablis, right? So can you give us the high level elevator pitch for the system first?
Okay, so I think with Chablis, we are going after geo distribution, right? And we have two goals. One is we want transactions that are able, like, that are local to one region to still have single region latencies, right? And at the same time, we want to be able to like do global, externally consistent lock-free snapshots without slowing down our like the regional rights in the system. So two goals, and they are in many ways like until this point were kind of conflicting.
Mm-hmm.
You either plus I think like so like that's the fast part. The general part just speaks for itself. You still want to be able to like run SQL, have an unrestricted API, and like all the nice general things. Now, geo distribution is an even harder problem than normal distribution. So like even systems that are like fast or general within the data center, when you deploy them as geo, they have even more trade-offs that they have to make. So let's take Spanner, right? Spanner was famous because of its TrueTime API, let you do externally consistent lock-free reads, and that's pretty big deal. Like you can just like do a global snapshot lock-free, fantastic, right? But it uses a specialized clock hardware, which is not like as widely available. Although there are startups and cloud providers that are trying to like make it more widely available, but still it's not like as generally available as you would like. And the other problem is that because of these TrueTime API, like every single write in Spanner has to wait out the clock uncertainty before releasing locks. So before committing, you have to wait out the clock uncertainty to generate version timestamps that are like guaranteed to have certain properties. Now, this clock uncertainty bound is many milliseconds in the Spanner paper. I think they have improved it recently, like maybe it's like 1 millisecond or something like that. But it still means that basically you have to slow down every single write in the system to achieve the lock-free snapshot reads. Some other systems basically require you to run consensus across the globe for every single write you make, which also kind of like slows down every single write in the system to let you like read lock free. And finally, so like these are the slow versions, right? And then the fast versions are based on determinism, which again sacrifices the generality of the programming model. So on top of like the fast and general trade-offs for the distributed transactions, when you go geo, you also get you have to sacrifice speed for generality, or generality for speed even more. Like there's more trade-off there. And what Chablis shows that you actually don't have to anymore. And I think like the pitch here is that you can have local writes have hundreds of microsecond latencies, and you can have snapshot free with external consistency, lock free in the same system. So it's fast and general. Now, of course, if you have to like run a transaction that spans the globe, that will be slow, but that's just like not avoidable.
Yeah, there's some fundamental sort of limit to how fast such a transaction can go, right? But it sounds there. Yeah, continue. Sorry.
No, I'm just saying, but reads, they can just go without impacting writes at all. So like that's the thing that we showed possible with Chablis.
Nice, awesome. So yeah, it really sounds like we can kind of have our cake and eat it here. So that's really cool. So I just want to just pull on one thread real quick, and you've mentioned it a few times whilst you've been talking about this notion of external consistency.
Yes.
So maybe you can kind of give a brief sort of rundown of what that actually means in practice.
Yes. So I think like it's also known as a strict serializability, although like some people slightly distinguish between the two. I basically just treat them as the same thing. So serializability, I think, is well understood. It means that like all the transactions you execute, the result is equivalent to some serial order. Okay, great. But it doesn't make any guarantees about which serial order. And one example here is that like basically like if you have a read-only query, you can always order it like as of the beginning of the database. Like you can always return null, right? And that would be still valid serializability because
it's a cop out, but yeah, it's technically still valid.
Beginning, you know, I didn't violate anything. It's as if it happened before all the other rights that you have. So that's obviously not very useful, and that's where the consistency semantics come in. And like these kind of tell you, like roughly, how stale like things can be. And the strongest semantics that you can give is like this external consistency, and it basically means that like if you start a read, you are guaranteed to observe all the writes that committed before you started that read in real time. Like, you know, if somebody, so basically like I can commit a transaction and then like, I don't know, call you on the phone, say, hey, you can read right now, and you go and execute it, and the system has to know that like to show you the results of my write because it committed before your read started.
Nice.
So basically, like even if the two transactions do not coordinate beforehand, the system is not allowed to order one before the other if one committed before the other started.
It's cool. It's got to respect the clock on the wall, right? It's got to
like physical time, basically. Yes.
Yeah.
Now, now transactions that are like that start overlappingly together may be ordered arbitrarily by the system. But if one committed before the other one started, it must be that the order will reflect that like that real-time relationship. And basically, like this is considered the gold standard semantics. And I think Spanner was the first like geo system that achieves it, but Kelvin and its successors also do.
That's the gold standard that with all these systems are aiming for. I just on a quick aside, I remember reading somewhere also somebody told me this, that the obviously when serializability is defined, there's no mention of actually like real time, right? Of sort of the wall clock time. But someone said that it's like it was almost they didn't have to think about it, because when they defined those semantics, like the notion of a geo-distributed system didn't exist almost. Like everything was on one box, right? So they just got that for free then. But then obviously, then now obviously the world's changed.
That's right. That's right.
Yeah.
Like when you think about like ACID, transactional semantics, and so on, it was all conceived on a single box, and so you got that for free because you are acquiring locks on things, and that just like orders things. But once you have replicas and global distribution and stuff, this suddenly becomes a major source of like surprises for
Yeah, that's one way of putting it. Yeah. Awesome, cool. Right, so let's dig into the details now of Chablis. But I guess before we do that, we need to give some airtime to its predecessor, Chardonnay. And I'm getting a theme with the names as well, so we need to touch on that at some point as well.
Yes.
But yeah, so like tell us about Chardonnay and how that then led to Chablis, and let's start filling in the details here.
Sure. So like I said, like I have known about the Spanner paper and the Kelvin paper, and I've been thinking about the trade-offs they both make, and I like conclude like, okay, it stems from slow two-phase commit. And then at some point I was reading another paper in NSDI 2019, I think. It's called ERPC, where it says data center RPCs can be general and fast. And it shows that like in bare metal data centers with like modern networks and things like kernel bypass and so on, you can really have RPC latencies that are 5 microseconds in the data center. Like, okay, that's interesting. That removes kind of one reason why two-phase commit is really slow. And then I came across a bunch of other like research on things like NVMe or ZNAND or like really low latency storage that are also single digit microseconds. And I was like, wait a minute, like it sounds like we can actually have very low latency two-phase commit right now. Like back of the envelope, like estimates, it's like if these numbers actually hold, there's no reason why you can't design a two-phase commit protocol that finishes in 50 microseconds or something. But a typical like SSD write is typical SSD access is 300 microseconds. Like commodity SSD, like not the fancy ZNAND or Optane ones. The one that cheap one that you want to use to store your data, it takes you like, I don't know, 300 microseconds to access. So suddenly the latency of one IO is actually higher than two-phase commit. And I was like, interesting. So maybe two-phase commit isn't the fundamental bottleneck that people think it is now. And what would you do, like, if that's the case? Like, what would the system look like? Can you finally be fast and general? And I mean, no shockers here. The answer is yes. That's the result of the Chardonnay paper. It was focused on single data center. The idea was, let's like make the assumption that two-phase commit is fast and design a system based on that. And what we wanted to achieve is not just low latency, but also the ability to handle high contention workloads. So, contention is where like one or a few records in the database become very popular, that they get most of the access. And it's something that's very unpredictable. Like it's very easy to like have an app where like the load is very like evenly balanced, but then suddenly something becomes very popular and you couldn't know before that. And once you have heightened contention, the slow systems basically, the performance just like really drops really bad. Like you either have very high abort rates because of deadlocks, or if you are using optimistic concurrency control, things just like assume that data isn't going to change, and then they try to commit, and the data change, and they have to like restart. So Chardonnay starts from the assumption that transaction IOs are slow, the network and the log are fast, and it does a few things. One is it uses the fast RPCs to support the log-free snapshot mechanism. And the way you do it is, like in Chardonnay, the key idea here is we have a service called the epoch service. It's a very, 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 very simple service. Its job is maintaining a single counter. That counter is not incremented by transactions. It is spontaneously, like on a timer, just advances. All right. So it's not a sequencer in the traditional sense where transactions would like go and like hit a number and that determines the ordering. No, it's just kind of a clock.
Okay.
But it's very coarse grained. And because transactions are only reading it, we can actually make it distributed and scalable. It's not a bottleneck. And that's a key difference from like sequencer-based designs. But the key point here is that like transactions, they run in very much the classic way transactions run in a shared nothing system. This is the root of the name Chardonnay because A, it's a sharded system. Sorry.
Okay, nice. Yeah. That's it. That's good.
And B, it's an architecture that's very classic that we think has aged like fine wine.
Oh, it's vintage. Yeah. Nice.
So in Chardonnay, transactions run using two-phase locking. Like these are things that were designed in the 80s or something, like by Jim Gray and Phil Bernstein and people like that. Very classic design. Shared nothing. You read you figure out, okay, like I need to read this key, then I'm gonna go to the partition server that has that key. I'm gonna take the lock on that key. In the end, I'm gonna like run two-phase commit to make sure that like everything is atomically committed. But we use like very fast RPCs, so then the network time is minimal compared to the IO time. And during running the transaction, during running the commit protocol, you just read the epoch. From the epoch service, you issue an RPC in parallel. You get the value, whatever value that was, is the value that you use to to version your records. And the system just maintains the property that like a transaction that reads an epoch value 5 is ordered before a transaction that reads an epoch value 6. And that's very easy to guarantee. We talk about the details in the paper, but it's easy to just make sure that happens because transactions still acquire locks and they are ordered. So like when a transaction finishes execution and it reads a value of the epoch, say 5, that means that it cannot have depended on a transaction that read a value 4. And why is that? Because it has the locks. If a transaction, value 6, and because it finished execution before reading the epoch, it knows that all its dependencies finished and read the epoch, and the value has been 5 or less. It couldn't have been 6. Does that make sense? Because the epoch is monotonically increasing by the system in real time. If you read a value 5, that means that anything you depended on had a value of 5 or less. It couldn't have been 6 because you read the latest value right now.
Okay. Yeah.
So that's nice, because that means that the epoch boundaries are consistent points in the order, and you can read their lock-free.
Okay. So you do your lock-free snapshot reads at an epoch version, basically. But I
Yes.
guess the one before the one that's the active epoch at the moment, is that how that would work?
That's basically right. That's basically exactly right.
Okay, so it reminds me very similar of a scheme like epoch-based memory reclamation. I can't say the word correctly. Reclamation. There we go. That's the word. And a similar sort of thing, right? About like kind of you get so far in advance with this epoch that nothing can have a reference to that epoch, something that in the previous bin, basically. So you can then garbage collect that. So it's a similar sort of concept, I guess.
It is very similar concept, and it was inspired by a paper called Silo. It's also it's a single node multi-core database, but we showed how to basically distribute it.
Awesome, cool.
But the nice thing is, if you want the property of external consistency, meaning any transaction that started before I did, that committed before I did, I want to observe it. All you have to do is wait for the epoch to advance once. Then you read as of the just before the new epoch, right? Because you know that any transaction that committed before you started has an epoch, say 7. So if you read everything that has an epoch 7, then you're golden. Nothing could have committed with a lower epoch. Very simple. Now, there are some technicalities when you are reading that we talk about in the paper, but that's basically it. Use the epoch to coarse grain version the transactions. So transactions can have the same epoch, right? And you would have to wait until after the epoch to read. But the epoch boundaries are the points where you do your lock-free snapshot reads.
Nice, cool. Now we'll probably, I guess, touch on this. Obviously, we've got to talk about Chablis and everything first, but kind of the how we actually choose this the time between these to increment these epochs. But maybe we can touch on that when we get to the results and stuff later on. But
that's a really good question. And in Chardonnay, it's not super sensitive. You just want it to be large enough compared to the transaction execution time, but small enough to not have the users wait for too long to get the external consistency read. So we set it to 10 milliseconds or even 5. We found it works well enough.
Nice. Cool. So I know, kind of now talking about Chablis, there was some challenges about taking this concept of Chardonnay in sort of the single data center and then kind of going geo-distributed with this. So can you tell us what these challenges were, and then we're gonna I guess talk about how you overcame them?
Yes. So basically, the problem here is that every committing transaction has to read the epoch, which is fine if all the nodes are in the same data center. But once you go geo, the question is, where do you put the epoch service? If you put it in one region, then all the transactions from the other regions have to take a cross-region RPC to read the epoch, which is bad because that would slow down the transactions in the other regions. And if you try to replicate it across regions, you still have to reading from the epoch service like basically has to be like a consensus read, because you have to get the absolute latest value. So then you're also running cross-region RPCs, which also slows down all your transactions. But remember, in Chablis, we want transactions that are like local to a region to have Chardonnay regional latencies. We're talking 100 microseconds.
Yeah.
So that's the conundrum. Where do you put the epoch service? And it turns out the solution is fairly simple. Because of the way the epoch service works, turns out you can basically break it into two. In every region, there is like an epoch, we call it the epoch publisher. And this looks to the nodes in that region like the epoch service looked before. It is the thing that they talk to read the epoch. And then there's one like central thing that can live anywhere that's actually responsible for advancing the epoch. So the way this works is we have this like global epoch service. It would go and say, okay, now the epoch is 5. It goes and pushes that value to all the publishers that are local to every region. And it does not advance the epoch again until all the publishers have gotten the new value. Now the publishers are designed to be like replicated, highly available services. So it's
I was going to ask kind of what happens if we lose one of these publishers, right? Yeah. Like, so there's some redundancy there as well.
Going down, that's fine because it's a replicated thing.
Okay, cool.
What this implies is that the value at every publisher can either be equal to the true epoch or one less, right?
Yeah.
But it turns out it's really easy to fix the algorithms to take account for that fact. And I don't want to go into like too much details, but the trick here is that when in doubt, you just need for the epoch to advance, and there will be no doubt.
Okay, so we just waited to get one more head, and then we know for sure that we're all good. We can't, because I guess everyone can only be at the latest one or the one before. So if you then get to the latest one, nobody can be. You can't be that one before. So then it's all good.
Absolutely.
Okay, I see. Nice.
And once you do that, suddenly you can read lock-free in a geo-distributed fashion. All the while, read-write transactions, they just read the epoch from the local thing using fast RPCs. They don't block. They don't wait on the epoch to advance. Nothing. It's just they keep the exact same latencies as before. You didn't need any fancy clock hardware. You didn't need like GPS clocks or anything like that. You didn't make any assumptions about the maximum clock skew. None of that.
Just did one number.
Just one number.
Yeah.
And it turns out it's easy to scale and maintain that one number. Like I said, like you have to make sure that like that one number is like, replicated
correctly,
it's durable and all of that, but it is not a scalability bottleneck, because you can have as many of these publishers as you want, basically. And it's not a latency bottleneck because you read it using like kernel bypass RPCs, in like even on public cloud, like not bare metal, you get today 20 microsecond latencies or so.
Yeah.
So this is something that's even like on cloud you can have today. You like nothing fancy, no clock, hardware, nothing like that. So fast and general, which was the goal.
Yeah, mission complete. So let's talk some numbers then, I guess.
Yeah.
So can you tell us about your experiments with Chablis and kind of what the results were? Yeah.
We ran a very simple experiment. Like we ran the YCSB benchmark to like measure regional latencies. And memory doesn't exactly serve me right, but I think like a single write would take like low 100 microseconds. Compared to Cloud Spanner, it would take many milliseconds. And then we run the snapshot read, the log-free snapshot read with external consistency and so on. And so to clarify, like this is a deployment across the US. So like we have a region in Central, in East, and in West US.
Yeah.
And you can like take a snapshot across those, I think, with external consistency and everything. And if memory serves right, I think like 80 milliseconds, like something like that, compared to Spanner, which is like 60 milliseconds. So it's a bit slower than Spanner because you have to like wait for the epoch to advance, but it's comparable, while our write latency is like an order of magnitude faster.
Nice. So yeah, I'd count that as a win.
I hope people will agree with that. Yeah.
Oh, some stuff. So I always like to ask this question as well. So this is like kind of, are there any sort of situations? So obviously we've kind of ticking these two boxes of fast and general, and it's are there any cases though when the performance of Chablis, or any use cases where the performance may be sort of suboptimal? I guess I'm asking here, kind of, what are the limitations of the system?
Sure. I do think like compared to something like Spanner, I don't think so, to be honest.
Okay.
But I think compared to something like Calvin or its Geo-Distributed successor called Slog, they're able to handle cross-regional writes more efficiently. Like if the system has lots of like cross-regional writes, the performance of Chablis will be fairly worse than Slog.
Okay. Yeah. So it can be sensitive to that aspect of workloads, I guess. So yeah.
Yeah. So basically,
Okay.
that like we make kind of strongish assumption that you don't do cross-region writes that often, but you care about cross-region reads. If that's not really true, I think like compared to something like Slog, the system would perform worse.
Okay, but obviously these other different trade-offs with Slog, right? As you said, alluded to earlier on, it falls into that fast category, but then we're probably giving up some
Yes, you will lose like the
generality of
programmability and
nice, cool. So I guess yes. So where do you go next with Chablis then? So what is the next step? Is there a next step?
There is a next step, and I think like so far, like in the paper, we kind of assume that we have like the geo partitioning of the data is static and known, but we want to be able, like, we want the user to be able to kind of like run a transaction that includes move this piece of data from Europe to the US, because you can, like, say you are a user of Facebook and you were living in Europe and then you move to the US, the app will want to move the data with you, right? So working on like geo partitioning and like making that a first class part of the system while supporting fast and general transactions, I think that's where we are going next.
Nice. This kind of concept of ownership, I guess, of like having the data move with the individual. It reminds me of just on a tangent, a system called, is it Zeus, that did something similar? Maybe, I don't know if it's on your radar, but maybe I'm getting it confused because with something
we're
else.
kind of like now like reading all the systems that
did something similar.
So it's just like there are like problems on like, okay, like how do you figure out where the data item is without running a geo-distributed query? Because so like there are all sorts of like fun problems here that we are thinking about. So that's certainly like one area that we are going for next with Chablis.
Yeah, that'd be really interesting to see, because there's a whole interesting space there, I imagine, of things to tackle. So that's cool. So my next sort of set of questions are sort of more sort of higher level and sort of general. So yeah, the first question is sort of kind of what impact you think your work on Chablis can have, and as sort of a software engineer, developer, data engineer, etc., how do you think I can kind of leverage those sort of findings of your work?
So I think there are two things here. One is the epoch versioning and like having the epoch service and so on. I think it can be useful in a lot more contexts. Like, ordering events and stuff like that, and just like it's something that comes up in a lot of contexts. So
Yeah.
I think like people can like look at this and realize this is exactly the level of ordering that I need. I don't have to order like every single transaction or event in the system with regards to each other, but like if I can like group them after the fact, opportunistically using epochs, then use the epoch boundaries to like read that. I think this is an idea that probably have more broader applicability. So that's one aspect. The other is just I really do think that databases that we have right now, they were designed in some way for like a different platform, a different hardware, a different era, and like there is a potential to just like have something that's just straight up better. And I'm hoping that like that kind of research, encourages people to revisit the assumptions. Something like, oh, Two-Face committed this like horrible bottleneck that we can't solve, or oh, we need these like fancy clocks to do like geo lock-free read, like that kind of thing. I'm hoping that like people can like look at this and realize, oh, like these assumptions no longer hold, and we can build like next generation systems that are better. And to facilitate that, I think we are working on releasing Chablis as an open source thing. So there's still some work there to move it from like research quality code to actual like things that
Production
people
grade, yeah, people can use.
would want to use, but it's something that will hopefully happen soon. So
Awesome. That'd be great to see how that progresses. Well, good luck with that. I hope it's a successful endeavor.
I hope so.
Cool. Awesome. Yeah. So I guess you've worked on this. I mean, how long was you working on this? When did the Chardonnay project start?
I think Chardonnay started in late 2021
Okay.
or
Yeah.
like early 2022, something like that.
Yeah.
It got rejected once before it got accepted, so that always.
It's a rite of passage. I mean, someone told
Yeah.
me once that I'm sure it's the Raft consensus paper, which obviously is been extremely influential. I'm sure that got rejected a couple of times before it was finally accepted.
Yeah.
So yeah, I mean, it's a lottery sometimes, right? The peer review system, but yeah.
The Chablis paper, thankfully, was well received from the start, but Chardonnay
Okay,
had
that's fantastic.
yeah.
So the question I'm leading up to is sort of across this sort of journey of working on these systems. What's the sort of like the most interesting lesson that you've kind of learned?
I mean, I really just think that like a lot of the like there's a lot of potential for just like looking at the conventional wisdom and like not accepting it as true. Now, it's not useful to just be contrarian. I think that's just not a good thing. I think it's important to understand why the conventional wisdom is the conventional wisdom. Like one thing that really drove me mad for a bit was just like people were saying, "Oh, transactions they don't scale." Okay, but why? Like, and like really, they didn't really have like
How have you arrived at that conclusion? Like, what's your thought
like
process? Yeah.
like sure, you tried running, I don't know, like MySQL and it didn't scale, but that really just doesn't necessarily mean that. And then, like so, it's important. Like what I would say to people who are like thinking about starting their own like research journey, it's really important to understand why the decisions were made in certain systems, because even though they may have been the best decision at the time, if you don't understand what went into them, you can miss out on opportunities where it's no longer the case. Like,
Mm.
Two-Face commit was genuinely a problem. It like the people who tried to avoid it like weren't misinformed or stupid. It
I'm
was
doing it for
really
the fun, right? Yeah, yeah.
it was really a problem, right? So it just so happens that I happened to stumble upon the fact that it's no longer an issue, and I can do some I can build a system based on that. The other lesson that's kind of like more practical, I think, or like more concrete, is that when you are dealing with on-disk systems, multi-core designs and single data center distributed designs can look surprisingly similar, and
Okay.
look for ideas in one to apply to the other and vice versa. So this is kind of like the whole like epoch thing was in many ways an extension or an application of the multi-core silo epoch. And it's very counterintuitive. Like you would think, okay, like this can only like work in a multi-core single node thing, but no, because the latency of disk is much higher than the network. Suddenly, a lot of the things that made sense in multi-core can make sense in distributed systems, and vice versa, I suspect. Like,
Yeah.
so that's just a thing that I that wasn't at all obvious to me like when I started, but it's just something that's like always in my mind right now. Like whenever I'm designing something now, I'm like, let me see what the multi-core people did about that, and maybe I can steal an idea or two.
Yeah, I like that. Oh, that's an interesting observation. I'm definitely going to keep that in mind as well. And I liked what you were saying about kind of when you use this conventional wisdom and like challenging the assumptions or reviewing those assumptions that were made to kind of get to that conventional wisdom, because you know what, the world changed, right? Things change, so maybe those assumptions are no longer valid assumptions anymore. The ball game's changed. But yeah, no, so I really like that. I'm going to jump over the next two questions just for the interest of time to get to my favorite question,
Sure.
which is about the creative process. And yes, I kind of want to know here, Tamer, how you go about generating ideas, and then once you've sort of generated a whole bunch of ideas, like selecting things to dedicate 2 to 3 years or however long to working on.
Um, I don't know. I'm very chaotic here. I wouldn't like it's not, but I think to me, the way I try to think about problems is just like really try to decompose the problems and figuring out why they are like, it's a problem because we do it that way. Okay, fine. But if we try to change this very small thing, how can I take that, and does it even like make sense, and so on. So I think, like, for example, I was like trying to figure out how to do block-free reads in Chardonnay, and I kept like banging my head against the wall for a few weeks trying to like change the right algorithm to make it work like in such a way to felt like it just like nothing really worked. But uh, but uh, but then I remembered the silo paper and I read it and I was like, you know what, this epoch thing is interesting. Why can't it work in a distributed environment? Like, and then I kept like, and then I couldn't like. There were two challenges that we solved, but there was no fundamental. Like, I was just like trying to kind of prove by contradiction that it cannot work in a distributed environment. Like, and then I couldn't prove, right? So at this point, I was like, maybe it can be solved. Maybe it's just, and then you sleep on it for a while, and like one day you get the epiphany. So that's kind of like how I like to do things. Really think about the problem, decompose it, read papers. Like I think just like in some ways there are very little new ideas under the sun. It's really just
This is
like
true. Yeah.
it, being able to recognize something from a different context and apply it in a new context can be very valuable. So that's really part of my creative process, is just like see if someone smarter than me figured something out, and see if I can just like cleverly apply it and make it work in a way that it didn't work before. So definitely standing on the shoulder of the giants is like,
That's the exact phrase I had in my head when you were talking then as well. Yeah, that's
yeah,
funny.
like
Yeah.
like trying to like reinvent the wheel, which is, I mean, to be fair, research is in many ways rewarded on very strong novelty. So that's kind of like
Yeah.
the incentives are structured in that way. But to me, I really like solving an important problem a lot more than coming up with a cool technique that may or may not be that useful. So that's just yeah.
No, it's a fantastic answer to that question, and it's another one for my collection. So thank you for that. It's great. I love to see how everyone has a different answer to that question. It's always interesting to see what people say and kind of get an insight into how you work, how your brain ticks, and what makes you tick. So yeah, awesome stuff. Cool. So it's the last question now. So what's the one takeaway you want the listener to get from this podcast episode today?
Transactions, they can scale, they can be fast, they can be general. Don't like you should expect more from your DBMS because it can do more for you.
I love that. What a great message to end on. Thank you so much, Tamer. It's been a fantastic chat.
Thank you so much for having me.
Brilliant. Where can we find you on socials? Are you on any of the platforms where the listener can go and connect with you or anything like that?
I'm not really. You? I think LinkedIn is the best way.
Okay, cool. We'll drop that in the show notes, and we'll put links to all of the work and everything we spoke about today in the show notes as well, so the listener can go and find that. But yeah, thanks again. And just a quick reminder, to the listeners, if you do enjoy the show, please consider supporting us through Buy Me a Coffee. It helps us to keep making the show. And yeah, we'll see you all next time for some more awesome computer science research.